And classes has officially begun. Welcome to second class of knot theory. Let me remind you what we did last time, very briefly. So we said, oh sorry, I was supposed to switch the camera to the wait, how do you do that? Here. Good. Not good. Oops. Sorry, we have technical difficulties. I'll fix it quickly. It worked before. I don't know why it's not working now.
Oh, that's a nice picture.
Yeah. All of this is happening while I'm recording. Start video. Okay, good. Okay, I don't know. You know, we can expect this, right? We're online, everything it depends on technology. Technology tends to mess. Okay, so last time I said knots. I didn't really define what a knot was, but I think it's basically unnecessary. And then a knot is equivalent, is the same thing as a knot diagram modulo an equivalence relation, and the equivalence relation is the equivalence relation generated by three relations. Why isn't this responding? Again, we're having a bad technology day, I'm sorry. Okay, good. So the Reidemeister 1 move, the Reidemeister 2 move, and the Reidemeister 3 move, and I will not repeat what they are. There's a long lag. I don't know what's going on today. Anyway. And then in order to separate the trefoil from the A-knot, we've defined an invariant lambda of D, the coloring number or the three coloring number of a diagram D, and it was defined to be the number of colorings of the arc of the diagram in three colors, red, green, and blue, such that no crossing displays exactly two colors. So right, in every crossing, if you look at the neighborhood of a crossing, then this is terrible. I don't know why this is so. Why we're so slow today. Sorry, I must debug this because there is a little bit it's just not working well enough. So one minute and I will hopefully, yeah, okay, I'm not sure what it is. Anyway, so at every crossing three arcs meet, right? One goes through and the two coming from the other sides. So there are potentially three colors. I'm not allowing you to count, or I'm not allowing you to look at colorings in which only two colors appear, exactly two colors appear at a crossing. So either the crossing is monochromatic, one color, or trichromatic, three colors. Okay? And then we computed that lambda of the trefoil knot is equal to 9, and lambda of the A-knot is equal to 3, and since 9 and 3 are not the same number, and since we have shown that this lambda is invariant, so we have shown that it doesn't change under Reidemeister 1 move and does not change under Reidemeister 2 move, and Reidemeister 3 move, actually let me circle in red, we didn't show it, so it's an excellent exercise for you. But anyway, since lambda is an invariant, and since 9 is not equal to 3, it follows that the trefoil is not the same as the R-naught. So I have two riddles or questions about this, okay? So one, and maybe I'll write them in red because I don't plan to answer them, and you can consider them as homework, okay? So question number one, for these two examples, lambda came out to be a power of 3, right? 3 and 9. And you're welcome to check a few more, and you'll find that it's often a power of 3. So the question is, actually let me start, okay, so is lambda always a power of 3? Sorry, we're having a terrible technology day, okay? And the second question is a bit harder to state, but but it's important. It's a subject that will recur, okay? So I always care about computing, right? Part of the point of knot invariants is to compute them on various knots so that you can tell them apart. So suppose you have a large knot, I don't know, like the R-naught that I've shown in a previous class. So I don't know, 50 crossing, 100 crossings. So 50 or 100 arcs. How long does it take to compute this coloring invariant? So suppose you have a knot with 100 crossings. So if you have a knot with 100 crossings, then you can expect that it will have roughly 100 arcs. And then each arc could be colored in 3 ways. So if you don't restrict your attention to legitimate crossings, then you have potentially approximately 3 to the 100 colorings. And 3 to the 100 is a very, 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 very large number. But of course, this will include the illegitimate crossings, the crossings that will display exactly 2 colors at some of the crossings. So my question is, if you wanted to count the legitimate crossings, the legitimate colors only, how long will it take you? So, I mean, one way to do it will be to look at all 3 to the 100 crossings, and then for each one to check if it's legitimate or not. That's relatively fast. But then you have to go over many, many, many possibilities. So my question is, can you compute lambda more efficiently? Okay? And I'm sorry, we're still having technical glitches. And let me, I suspect it might have to do with somehow the screen share is not working. So let me stop the share and then restart it, and then hopefully this will be better. Okay, so...
Professor,
yes.
If this display detects your writing using the internet, it might be an internet connection problem.
No, it's not using the internet. Okay, I'm trying again. And wait, am I sharing the right screen actually?
Yes, we see the share.
Okay, good. So let's hope that actually it's not promising. Okay, anyway, one further thing to say is that this is a horrible invariant. It's a lousy invariant, okay? So I mean, these are good questions and we will look at it more because it has some good sides to it as well. But basically, for most knots, the vast majority of knots, the values are either 3 or 9. And then occasionally there is a knot where the value is 27, okay? But that means that you really can't tell knots apart using it. For example, you cannot tell the mirror of the trefoil from the trefoil because they have clearly the same three colorings, okay? So I want to start looking at a better invariant, and the better invariant is the so-called Jones polynomial, and I have to start with sad news. So Von Jones passed away. Okay, he's the person who invented the Jones polynomial. He in fact got a Fields Medal for it, and he passed away just earlier this week. So, and he was a good friend of mine, and actually I took this picture when he visited me back when I was in Jerusalem. So we went to the Dead Sea, and the Dead Sea has like 30% salts dissolved in the water. So the water is extremely heavy, and so you can basically sit on the water and read a book. And this is Von Jones demonstrating it, and I'm afraid he is no longer with us. Anyway, his invariant is still with us, except I want to describe it not the way Jones discovered it, but the way Lou Kaufman, another well-known mathematician, simplified it a few years later. So, oh, this is so much faster. So so I want to tell you a little bit about the Kaufman bracket, and it's called the Kaufman bracket because it's an invariant of diagrams. So you put a diagram inside a bracket, and then that's just the notation for the invariant. I don't know, not a very imaginative choice of names. Sorry, we need another page. Maybe I should learn to add lots of pages in advance. But that will be next time. So the Kaufman bracket is defined by two axioms. So axiom number one, axiom number one, if you have a crossing, then there are two ways of so-called smoothing it. Smoothing it is, well, I'll immediately show what it is. So smoothing it is replacing it either by this figure or by that figure. They're sometimes called the vertical smoothing and the horizontal smoothing. But actually we're in topology, so the vertical and the horizontal are only an artifact of the way my screen is placed. They don't have a real meaning. So sometimes they're called the zero smoothing and the one smoothing. And I don't have a very good way of remembering which is which. Basically, the zero smoothing is, so I think of it as the node as an interchange, a highway interchange, and I call the lower strand, I say that it is level 0, and the upper strand is level 1, and then the zero smoothing is what you get if when you enter the interchange at level 0, you turn right. So I enter at level 0 and turn right, and or I enter from the other side at level 0 and turn right, and I'll get these two lines. And the one smoothing is if you enter at level 1 and turn right. So if I enter at level 1, I enter here and turn right, I come out here, that's this line. Or if I enter on the other side at level 1 and turn right, I come out there, which is that line. Okay? So I haven't yet described the axiom. The axiom says that this is equal to A times that plus A inverse times that. Where A is a certain variable that I haven't specified yet. Okay? So now suppose you have a complicated knot. Every place you see a crossing, you replace it by a smoothing, and there are two possibilities for each smoothing to replace it with, and each one comes with a different coefficient. Well, one with A inverse. And but after you do it to all crossings, you get a knot that has, or a diagram that no longer has crossings. If it no longer has crossings, then it's a union of circles. And then the second axiom is that if you have a union of k circles, or in general, if you have a circle and then a diagram, then the bracket of the circle with the diagram is equal to d times the bracket of the diagram, where d is, again, some variable that I'm yet to specify its meaning. So maybe we should do a quick example. So, example, let's compute, bad technology day. So let's compute the Kaufman bracket of the so-called Hopf link. So the Hopf link is the picture that looks as follows. So notice that this actually is not a knot, right? We defined a knot to be a circle in R3. This is a pair of circles in R3. Well, this is, well, a new object, but I think I don't want to precisely define it just as much as I didn't precisely define knots. Basically, you embed two circles in R3. There is a similar diagrammatic theory with exactly the same with exactly the same Reidemeister theorem to state. And in fact, this particular link is called the Hopf link. Anyway, yeah.
May I ask a question? Or?
Sure, of course.
So the bracket distinguishes between the two topologically identical smoothings?
Sorry, they are not topologically identical. So the meaning of this picture, okay, maybe I should have explained it. So I am drawing what you do in the vicinity of a single crossing. But this crossing is connected to the rest of the knot. Okay? So, and when I draw these pictures, I mean, I am telling you what happens near the crossing, nothing happens in the rest. Okay? So, for example, yes, okay. So, for example, if the rest of the knot was extremely simple, so if this was connected to that, and this was connected to that, then I would mean, then the Kaufman bracket would be computed by replacing the crossing with a 0 smoothing or a 1 smoothing. In the case of a 0 smoothing, the connection will be like I wrote. In the case of a 1 smoothing, the connection will be, again, I'm only modifying the picture, so the rest remains the same. I'm only modifying the part that's shown, so the rest remains the same. So here, so here I get a single component at the end, and here I get 2 components. So in fact, so in a way we've already done one example. We have just figured out that the Kaufman bracket of a picture that looks like the number 8, right? This looks like the number 8, is equal to, so the Kaufman bracket of 8 is equal to A times, this is a single circle, so it's D. So A times D plus A inverse times D squared. I suppose I should have added, the way I wrote it, I should have added another axiom that the bracket of the empty picture is 1. Okay? Anyway, so let's go back and compute the Hopf link. So for the Hopf link, I need to replace the top crossing either by a 0 smoothing or by a 1 smoothing, and I need to replace the bottom crossing either by a smoothing, or either by a 0 smoothing or by a 1 smoothing. There is a total of 4 possibilities, right? Either 0, 0 or 0, 1 or 1, 0 or 1, 1. So let's write these 4 possibilities. So the 0, 0 smoothing looks like, let me draw it. So let me say that I start here. I enter this crossing at level 0 and turn right. So, so the first crossing gets smoothed, the top crossing gets smoothed like that. So this is the 0, 0 smooth case. The bottom crossing is, so I enter from the 0 level and turn right, so it's the same. It gets smoothed like that. And then I need to connect the ends the way they were connected before, so I get this picture. I hope I got it right. I think so.
No, the ends should be connected the left and the right, not top.
Oh, you're right, you are right. The ends should be connected on the outside, it should be connected like this, left and right. Thank you. Okay? Anyway, now let's do the 0, 1 smoothing. So the 0, 1 smoothing, I have to flip the bottom one from a 0 smoothing to a 1 smoothing. So the picture looks like, well, the bottom one looks like this, and then I have this and that. And then I have the 1, 0 smoothing. So in the 1, 0 smoothing, I do the same at the top. So I get a picture like this. And finally, I have the 1, 1 smoothing. So the one smoothing, I replace both, and then the picture will look like, well, both of them look like this, and the picture is this. Okay? Anyway, so what's the invariant? Okay, here I get so let's compute it. So this should have come with a coefficient a squared, right? Because I did 2 zero smoothing. So this comes with a coefficient a squared. This, oh my God, I'm sorry. Sorry, I'm just having a bad day. I didn't want to tell you that b is a squared. I wanted to keep the coefficient of the one smoothing just as a variable. So let's call it b. So over here, I'm sorry, I'm just messing up today. So so here again, it's not a inverse, it's b. Just another variable. So here I have a squared. Here I have a times b. Here I have again zero smoothing, one smoothing, so a times b. And here it comes with coefficient b squared. And the overall answer is a squared times, here I have 2 cycles, so a squared d squared, plus both of these have only 1 circle at the end, so it's ab times d, both of them, so twice a b d, plus, and here I have a b squared and 2 circles, so plus b squared d squared. Okay, good. So is this an invariant? Okay. So so I've shown you some silly definition with silly computations, but if it's not an invariant, what's the point? So is this an invariant? So let's start. Let's compute the Kaufman bracket of the left-hand side of a Reidemeister 2 move. Note that this is not what I wrote before. In the Hopf-Link, the crossings are arranged slightly differently. Here you cannot detach the 2 components, and here you can. So let's compute the Kaufman bracket of the left-hand side of a Reidemeister 2 move. What do we get? So again, I have 4 possibilities. Let's write all of them. So the 0 at the top, 0 at the bottom possibility, so I get a squared times the bracket of this is what I get at the top, and this is what I get at the bottom. Okay? Right? At the top I do a 0 cross smoothing, so I go to the right at the crossing, and here I go to the right. Yeah, this is it. Plus a times b times, so if I do if I flip the bottom crossing, I get a picture like this, plus again a times b. If I flip the top smoothing, I get a picture like this. So the bottom stays as written, and the top get flipped, so it looks like this. And finally, if I flip both, I get a picture that I get b squared times, so I flip the top so it looks like this, and I flip the bottom so it looks like this, and that's the picture. Okay? But now, here I have an independent circle. An independent circle is worth a factor of d. Okay? So overall, I have that this thing is equal to, so let's see, this term and this term are actually the same. Okay, topologically they are the same, and again, it matters how do they connect to the outside, but they are the same even inside. I mean, whichever way this will connect to the outside, it will be the same as that. You'll get the same result as that. Likewise, this one, if you remove the circle, it's still the same. So all of these three terms combine together, and I get, well, a squared plus, from here I get b squared plus, from here I get a times b times d, and all of this gets multiplied by the bracket of this picture. And from the remaining term, I get AB times, well, topologically all of these curls don't matter, so it's A times B times that. But now I want it to be equal, right? If you the other side of the Reidemeister 2 move is precisely this picture. So I want the left-hand side to be equal to just this, but this forces me to set two equations. It forces me to set A times B is equal to 1, and A squared plus B squared plus ABD. So again, in the other side of the Reidemeister move, this will not appear. So I want its coefficient to be 0. So I want this to be equal to 0. But this implies that B is really A inverse, as I wrote in the beginning and revealed the secret, sorry. And from here, so if you substitute A is equal to B inverse and put it in this equation, you find that D is equal to negative A squared negative A to the negative 2. Okay? So we started with something that might have depended on 3 variables, and now we find that it actually depends on only 1 variable, A, because the other 2 variables can be expressed in terms of A if I want it to be an invariant. But let's see if we're lucky. Is this going to be an invariant? So now I have to check if it's now I have to check if it's invariant under Reidemeister 3. So something lucky happens, and Reidemeister 3 is actually easier than Reidemeister 2. Okay, so let's try that. So let's compute the bracket of the left-hand side of a Reidemeister 3. So this is the left-hand side of a Reidemeister 3, and let's try to compute the bracket. So a priori, it seems like a hard computation because there are 3 crossings, which means that there are 8 smoothings. And drawing 8 smoothing is, well, it's just going to take me a lot of time. But there is a clever trick. we only expand this crossing. Okay? So if I expand the top crossing, I get that this is equal to, sorry, I didn't leave a space for the coefficient. So this is equal to A times what you get when you replace the top crossing by a zero smoothing, and that's a picture that looks like the following. It's this picture. Plus A inverse, well, I should have...
The zero smoothing is the other way.
No, oh, you're right. You are right. It actually doesn't matter, but you're right. So this is the zero smoothing plus A inverse times the one smoothing. The one smoothing is the picture I just drew before, so it's this picture. But you see, topologically, I mean, I can slide the lower line below this sort of the smoothing point, and I'll get that that this is equal to A times this. These two pictures are simply the same. Plus, well, I've already shown invariance under Reidemeister 2. So in principle, I should have expanded this to four smoothings. But I don't need to because I've done it above. Okay? So I know that this is invariant under Reidemeister 2, so this one is in fact equal to, I can slide the horizontal strand to be between the two other ones, and then I can slide it further below the top one. So overall I get plus A inverse times this picture. But you see, this is exactly what you get when you compute the bracket of the other side of the Reidemeister move. So this is exactly the bracket here. Because if you take this bracket and expand only the middle crossing, the bottom, the lowest crossing, you'll get A times this plus A inverse times that. So we've shown invariance under Reidemeister 3. It would be highly disappointing if we don't get invariance under Reidemeister 1. Okay?
Sure,
Yeah?
just one comment.
Yeah?
I think the rightmost bracket picture, you flipped the sign of the crossing.
Oh, I did. I did. Right. So, and of course, the way I wrote it, it's wrong. It should have been this. You're right. Sorry. Yeah.
Also, I think the screen share has stopped updating, but we can still see your camera.
I don't have a good explanation for why the screen. We're having a bad technology day. I don't know what to say. Everything looks normal. Should I? If somebody will tell me that I should restart the screen share, I will. But otherwise, I'll just keep it this way. Okay. Good. So it will be disappointing if we don't get invariance under Reidemeister 1, but we'd better check it. Okay? So let's compute the bracket of a Reidemeister 1 left-hand side. So, again, we get A times the zero smoothing is this, I believe. and the one smoothing is, wait, the zero smoothing is, no, that was the one smoothing, sorry, so it's A inverse times this plus A times the zero smoothing. So the zero smoothing is, if I come here, I turn to the right, so I get an independent circle over here. Okay? And this is equal to, so here I can erase a circle and replace it by D. And here, I mean, I can just pull this line tight. So in both cases, I get the line that I expect to get from a Reidemeister 2 move, from a Reidemeister 1 move, sorry. But in the first case, it comes with coefficient A inverse, and in the second case, it comes with a coefficient A times D. So it comes with a coefficient A times negative A squared negative A to the minus 2. And if we're lucky, this simplifies to 1. And let's check, are we lucky? So the A inverse cancels the A inverse times the A inverse here. Wait, something is wrong. Oh yeah, no, it's fine. Right, sorry. So the A inverse cancels the A times the A inverse, but nothing cancels this. So I get this times negative A cubed. And in fact, you can check, so okay, we should be very disappointed, but here's a little secret about knot theory. If there are issues only with Reidemeister 1s, usually you can find a way around them. So let's find a way around here, okay? So I should have said that there are variants of a Reidemeister 1 move. So I wrote one variant, but there is also the second variant where the picture looks like this. So it differs by the sign of the crossing in the middle of the, to the left of the kink, okay? So if you compute this, you'll find that you get a single line times negative A to the negative 3. Okay? And then the idea is to look for an invariant that changes. So the way you resolve a difficulty like that is that you look for an invariant that changes in the opposite way. So this invariant changes by multiplication by negative A3, if you do a Reidemeister 1, or by negative to the A to the minus 3, depending on the kind of the Reidemeister 1. So what you do is you look for an invariant that has the opposite behavior. Okay? And then you multiply the two and you get two invariants that don't change. You get a product that does not change. So how do you do that? So you define a new thing, okay? You define a new quantity. So you define the Reith of a knot diagram. So the Reith of a knot diagram, this is Reith, to be the sum over all crossings x in D of the sign of the crossing. So let me define the sign of a crossing. So if you have a crossing, well, so far, up until now, I wasn't careful about the orientation, or I didn't care about the orientation of the lines. And now I have to start caring. So if I have a crossing in which the lines are oriented as follows, then its sign is declared to be +1. And if you have a crossing in which if you have the opposite crossing but with the same orientations, then its sign is declared to be -1. Now, how do I tell these apart? So if you've seen how electromagnetism works, it should remind you. You should be reminded. So basically, you grab the upper strand with your right hand, always with your right hand. Sorry for the discrimination against left-handed people. So you grab the upper line with your right hand, and so that your thumb is pointing in the direction of the flow. And then your fingers point at the direction of the flow of the lower line. And over here, if you grab the upper strand with your right hand so that the thumb is pointing in the direction of the flow, your fingers will be pointing in the opposite direction. So that's a +1, that's a -1. And by the way, it doesn't matter which strand I grab. So if I grab the lower strand so that my thumb is pointing in the direction of the flow, my fingers are still, the side of my fingers that faces the upper strand is still pointing the right way. Okay? So basically, if you have a crossing and you want to determine its sign, you grab one of the strands so that the thumb is in the direction of the flow, and you see whether the fingers are pointing with or against the flow of the other strand. Okay? So, is the right an invariant? So, I need to check the 3 Reidemeister moves. So let's check Reidemeister 2. But now I have to take oriented strands. If I orient the strands, this crossing is a, let me see, a negative crossing, and this crossing is a positive crossing. So this configuration will contribute 0 to the right. I sum over the signs of all crossings, so this configuration will contribute 0. So the right of this is the same as the right of that. What about Reidemeister 3? So let me let's write a Reidemeister 3 move. So, so here is the left-hand side, and here is the right-hand side. And in fact, I don't even have to check what are the rights, because this the crossing number 1 here is the same as crossing number 1 here. In fact, they only differ. In fact, they're somehow literally the same. They don't even see the fact that the third strand has moved. Okay, so 1 is equal to 1. Crossing number 2 here is the same as crossing number 2 here. And crossing number 3 here is the same as crossing number 3 here. So it doesn't even matter how the strands are oriented. They can be reoriented whichever way they want. The sign from here and the sign from here are the same. The sign from here and the sign from here are the same. The sign from here and the sign from here are the same. So the right of this is equal to the right of that. And we have invariance under Reidemeister 3. But now if we don't get invariant under Reidemeister 1, that will be good news. Because it means that we found an invariance that has the opposite, or we find a quantity that has the opposite behavior. So next class we will find we will assemble the two invariants, the two quantities together. And I'm sorry, today was a slow-moving class with glitches. Hopefully I'll fix them by next time. So see you on Monday. Yeah.
A question.
Yeah.
So in determining the value of B, you started so you used the second move to determine the value of B.
Yeah.
In setting up everything. So could we have used say either Reidemeister 3 or 1 to determine the value of B, and things would have moved in a different direction?
At the end, the value of B and D that we determined work for both Reidemeister 2 and Reidemeister 3. So, if we had done it the other way, we would have gotten something that also works for both Reidemeister 2 and Reidemeister 3, so it must be the same. So, I mean, if you try to figure out what to do to get invariance under Reidemeister 3, I'm not sure what you will get, but after that, if you will impose the conditions for Reidemeister 2, you'll end up imposing the same conditions, the same two conditions, Reidemeister 2 and Reidemeister 3, so you'll have to get the same answer.
Okay.
So maybe it will be a more complicated path, but you'll get the same answer.
Okay. And you spoke about the variant of Reidemeister 1.
So Reidemeister 1 fails, and we're in the middle of fixing it.
I suppose we could also force A to be equal to 1.
Right, so maybe I should have said that. We could have chosen a cubic root of -1 here. If A is a cubic root of -1, we also get invariance for free. The resulting invariant comes out not interesting.
Okay.
Okay.
I'm interested in a maybe somewhat philosophical question about this polynomial of like why does the polynomial even work? What does multiplication encode and what does addition encode, and why do they work just nice in this way that gives us an invariant? Is there a reason for this?
I feel uncomfortable about answering this because we're already 3 minutes and 47 seconds past the ending time. Ask again next time.
Okay.
Okay? Okay, so let's quit, and again I'm sorry for the glitches today, and hopefully we'll do better next time. Bye.